morning to Dr. Sufyan and everyone. We are Group 6 from KM44203 Heat Transfer. Our project is entitled The Design of an LPG-Fired Indirect Air Heater System for Controlled Drying of Biomass. So today we'll present the design concept, engineering calculation, computational fluid dynamics CFD simulation results, and the advantages of our proposed system. So the problem statement of this project are, firstly, biomass normally contains more than 90% of moisture, so it requires controlled drying before storage or further processing. However, drying temperatures above 70 degrees Celsius can reduce biomass quality. And adding on to that, existing direct fired dryers also expose biomass to combustion gases, which may contaminate the product. And therefore, an indirect heating system is proposed to provide clean and safe hot air. Moving on to the objectives. The objectives of this project are, firstly, to design an LPG-fired indirect air heating system. Secondly, to maintain the drying air temperature below 70 degrees Celsius. Thirdly, to implement temperature control using sensors and airflow. And finally, to validate the design using engineering calculation and computational fluid dynamics CFD simulation.
Based on our design requirement, the system is designed to process 1000 kilo per hour of wet biomass with an initial moisture content of 90% and reduce it to 50%. LPG is selected as the heat source, while a fin tube heat exchanger is used to separate combustion gas from the drying air. The drying temperature is limited to 70 degrees Celsius, and several safety systems such as flame protection and gas leak detection are included.
Next, for our system design overview, the burner generates hot combustion gases which flow through the separating tube. Heat is transferred through the fin tube to the clean air supplied by the blower. Since combustion gas and drying air never mix, contamination is avoided. Finally, the hot enters the drying chamber while combustion gases exit through the flue. For our component selection, the main components include an LPG burner, fin tube heat exchanger, stainless steel tube, aluminum fins, blower, duct chamber, and air inlet and outlet. These components were selected because they provide good heat transfer, corrosion resistance, safe operation, and efficient airflow.
Next, I will explain the heat exchanger design. After calculating the total heat duty, our next step was to determine the required heat transfer area. Based on the calculation, the required area is 67 meters square. After including a 50% safety factor, the final design required becomes 78 meters square. To meet this requirement, we adopt a modular design by using 18 identical heat exchanger modules. Altogether, this module provides a total heat transfer area of 366 meters square. Finally, we perform the design check by comparing the required area and the actual area. Since 366 meters square is greater than 78 meters square, the design has sufficient heat transfer area to meet the required heat duty. This means our heat exchanger set is safe, variable, and suitable for the drying system. After confirming that our design meet the required heat transfer area, we finalize the heat exchanger design. The final design consists of 80 stainless steel tubes and 49 aluminum fin plates. We choose stainless steel for the tube because it's durable, can withstand high temperature, and has good corrosion resistance. For the fins, we selected aluminum because it has excellent thermal conductivity, allowing heat to transfer more efficiently to the drying air. Overall, the combination of these materials and dimensions give us a compact heat exchanger with efficient heat transfer performance. I think that's all from me. Thank you now. And now I will pass the presentation to Aiman, who will explain the CFD simulation result.
So this is the heat exchanger that we modeled in SolidWorks, shown here as an exploded view so you can see all the parts. At the bottom is the blower that draws in ambient air and pushes it upward. The air rises through these aluminum fins, which is where it picks up the heat. Running through the fins are the serpentine tubes that carry the hot combustion gas. The gas flows the opposite way to the air, so heat crosses the tube wall from the gas into the air, but the two never actually mix. That's what keeps the drying air clean. At the top, the warm air leaves through the duct, and the combustion gas exits separately through the flue. So the whole idea is simple. Hot gas on the inside of the tubes, air on the outside, heat crossing between them without contact. So to check the design works, I ran a CFD simulation in SolidWorks flow simulation. So we modeled the air side, set the inlet airflow to 1.3 kg per second, and fixed the tube wall temperature to represent the heat coming from the gas. I ran two cases. The one on the left is the burner at full fire, wall at 200 degrees Celsius. This is no control. The air comes out at 99.6 degrees Celsius, nearly 30 over our 70 degree limit. That would scorch the biomass. The one on the right is with control. The wall held at 100 degrees Celsius. Now the air leaves at 58.4 degrees, safely under the limit. With the same geometry, same airflow, the only thing that changed is how hard we fire the burner. That's the main result. It's the heat input, not the airflow, that keeps the air below 70 degrees. The simulation also gave a low pressure drop of 128 pascals, which means the blower uses very little power.
This slide highlights the advantages of our proposed design and system compared to the existing system. Firstly, the existing system uses direct fired heating where the combustion gases come into direct contact with the biomass. This can affect product cleanliness and may introduce smoke or contaminants into the drying chamber. In contrast, our proposed system uses indirect fired heating with the fin tube heat exchanger. The combustion gases transfer heat through the heat exchanger while only clean heated air enters the drying chamber. This improves product quality and makes the drying process more hygienic. And another improvement is the heat transfer performance. The existing system has relatively lower heat transfer efficiency, whereas the fin tube heat exchanger in our design provides a larger heat transfer surface area, allowing heat to be transferred more effectively. Furthermore, temperature control is also significantly improved. Traditional systems often experience fluctuating temperatures, making it difficult to maintain suitable drying conditions. Our design incorporates a PID controller that automatically regulates the drying temperature and keeps it below 70 degrees Celsius. This helps prevent overheating and preserve the quality of the dried product. And finally, the existing system has a fixed design, which limits feature modifications. Our proposed dryer features a modular design, making it easier for assemble, maintain, and upgrade for different drying capacity or applications. So overall, our proposed system offers 5 key advantages: clean drying air, improved heat transfer, stable control below 70 degrees Celsius, enhanced operational safety, and smart modular design. These improvements result in a more efficient, reliable, and higher quality drying process.
Hi, now I will present about discussion and validation for our project. Looking at our discussion and validation, a massive 96% of our total 659.32 kilowatt heat duty goes entirely into the latent heat of vaporization, meaning we are mostly evaporating water. Because of this, simply changing the airflow isn't enough to control the temperature. Instead, we must use active regulation by adjusting the LPG gas valve. Without control, the drying air peaks at a dangerous 112.1 degrees Celsius, which would ruin our biomass. But with our active PID control, the temperature drops safely to 62.8 degrees Celsius, which is giving us a comfortable 7.2 margin below our strict 70 degree Celsius safety limit. Next, to handle this heat demand in the real world, we use a modular design. By connecting compact fin tube modules in parallel, we gain mass manufacturing benefits and great system redundancy by dividing our total duty by one module's output of 37.18 kilowatt. We found out we need exactly 18 modules. We also optimized the physical geometry, originally tied 3.75 mm fin spacing, caused heavy back pressure. By widening the spacing to 8 mm, we cut the pressure drop 54 down to just 128 Pascal. This slashed our blower power demand to only 3.92 kilowatt while sacrificing the less than 8% of our heat transfer area. In short, our 18-module system successfully and safely delivers the required heat while keeping temperatures well below the critical 70 degrees Celsius ceiling. That's all from us. Thank you.